My name is Mawata. I've been a learning tree instructor since the year 2000, and I've written more than 40 courses for learning tree. I've also worked as a professor of mathematics at the University of Tennessee in Chattanooga and published papers in mathematics, machine learning, and visualization. I want to continue our conversation about anomaly detection, and this time let's talk about unsupervised anomaly detection. So what is unsupervised anomaly detection? Well, rather than training a model on labeled data, that humans have looked at and decided it is of one class or another, in our case, normal or abnormal, this time we're going to just give the model the data that we wanted to categorize without having a prior training session. Now, we do need to give it some other hints. Typically, it will be things like similarity measures. We need a number that tells you how far things are from each other. So what kind of methods do we have to do this? Well, common approaches are based on clustering, which is, of course, a big area of machine learning. Then there are some that are density-based, essentially trying to spot places where you have a lot of your data points and places where they seem to be all alone. And then there are tree-based algorithms, which will recursively apply some kind of operation to break up your data until you get the desired result. So when we talk about cluster-based anomaly detection, we're going to use any of the regular clustering algorithms that we have in machine learning. Data points that are similar will be considered to be in a cluster, and if 2 points are not similar, they should be in different clusters. So if you have your data and you cluster it, what you hope is that the big clusters will be the normal data, and we assume that the abnormal data is relatively rare, so it might be in smaller clusters or maybe just isolated points that don't even have neighbors close to them. This is going to work as long as that type of anomaly is not common. If it is common, it might very well form its own cluster, and then, of course, you wouldn't be able to detect it in this fashion. Then there are density-based anomaly detection methods. So this time, you assume that if I have a point that is normal, there will be other points in a close neighborhood of that normal data point. So you might decide to set a certain threshold and say, if you are a normal point, there should be so many other points that are within that distance of you. So essentially, you're going to be looking for points that are kind of far away from everybody else or far away from most of the other data points, and you're going to say that those are probably going to be outliers. Let's take a look at a few algorithms in a bit more detail. And the first one that I'm going to describe to you is called isolation forest. This one is a tree-based one. So it's going to be a divide and conquer type of approach. Break up your data, break up your data, break up your data, and hopefully you'll be able to figure out the anomalies and the ones that are not anomalies. And what we do is we create an isolation forest, or we sometimes abbreviate it to iForest, by just randomly dividing our data. The idea being that the points which are way out there on their own, they'll be cut off very quickly because there's nobody close to them. And the points which are close to each other will take a few more rounds before they get, isolated from everybody else. So let's have an example that we can actually do visually. Now, because I want to be able to draw this example on a two-dimensional screen, we're going to just have two features so that we can then have a point that has a certain value of one feature and a value of the other feature. Let's just call them X and Y, because then it's easier to remember. Choose a value and just slice our area using that value. Well, you see the little blue line towards the bottom? It looks like when we chose a value of Y, it was rather low and all the points are on one side. So we haven't really broken up our data, but we now have a smaller rectangle to deal with. Now the rectangle below, the very thin rectangle below, that's no longer worth dividing because, well, there's nobody to isolate down there. So we shall just leave that alone, and we shall look at the larger rectangle, the top one. Pick one of your two features, pick a value that makes sense, something between the minimum and maximum value of that feature, and slice. So it looks like, once again, we chose the Y feature, picked a value between the minimum and maximum value of Y, slice. Well, we've got 2 points that are below, and the rest of them are above. Now we want to keep doing that until we get cells that have single points in them, or we shall say we have isolated that point. So let's do it once again. And you'll notice we divided the bottom one. Well, D and F are still together in the same cell. In the top one, this time it shows a point, a value where E, B, and L are in one cell and the other points are above. Okay, so let's keep doing that. So here's a fourth division. And you can see that the cells are getting smaller. Now, when you look at the fifth time we do it, notice that the point M has been isolated. It is in a cell of its own. Now, we're going to assume that the tendency will be that the points which are far off will tend to be isolated earlier in the process. Let's keep going once again. And let's do a seventh time. Now, if you notice, D and F have been isolated because they are alone in their own cell. So we have B isolated at the seventh iteration, same thing with F, whereas M was isolated at the fifth iteration. Okay, keep doing that. And we shall just say, keep slicing, slicing, slicing. And when we get to the 12th division, all the points have been isolated. Now keep a record of when the isolation happens. Now, because we're choosing the features and the values at random, it means that every time we do it, we'll get slightly different numbers. So why don't we do it a whole bunch of times? This is what happened when we did it 100 times, and then we took the average of the number of iterations it took to isolate the points. So we have the point M, for example. It took, on average, 6.19 iterations to isolate it, and you can see the point F took 5.09. Now, the thing I want you to notice is that the points which are kind of close together, like think of A, C, G, E, B, and so on, they have higher numbers. It took more cycles to isolate them. The points which are kind of on their own, like M and F, didn't take as many iterations to get isolated. Now, notice J and H, they have high numbers, and when you think about it, one person could say we should consider J and H to be strange points because they're way up there. But if we're using this method, it's going to take a while before you manage to go right between J and H and isolate them. So they tend to get higher numbers. Okay, so once we've done it a few times, like in this case, we've done it 100 times, the next thing we want to do is to say, let's pick a threshold. In this case, I picked a threshold of 7. And let's say that if it took less than 7 iterations on average to isolate a point, which is the case with the points F and M, we're going to consider those points to be the outliers. The next approach that we're going to talk about is going to involve distances between the points once again. And there's a concept I want to talk about before we go into the algorithm proper, which is the idea of a k distance. And here's how it works. You're going to choose a number that we shall call k. And just to have something in mind as we discuss these algorithms, let's say that we choose k to be 4. That way you can have a picture in your mind of what's going on. So for a point in our data, let's call the point P, then the k distance of P is going to be the distance to the furthest one of its k nearest neighbors. Let's think about this. If I say my k is 4, remember we're taking k to be 4, and you have one of your data points, I'm going to say how far is the closest one, how far is the second closest one, how far is the third closest one, how far is the fourth closest point. That distance, the distance from the point I'm thinking of to the point that is fourth in distance from that point, is going to be the 4 distance of that point. Now, this will be even clearer if we run through a few examples. So why don't we set up a little example? So let's consider the point A. And remember we said that k is going to be 4. All right, so if we have the point A, then the closest point to A is C, all right? So C is the first neighbor. It's the distance 1 from A. Then you've got 2 points that are second. So you've got B and L. Let's take them to be the second and third neighbors. G is A's fourth neighbor, and the distance of G from A is 2. So we shall say that the distance of A is 2. As a second example, let's take a look at the point J, which is way up at the top. And we want to get the distance of J. So from J, we're going to say the 4 closest points. Well, we've got H, which is just 1 unit away. Then we've got M, and we've got A, and we've got L as the fourth one. Okay, so L is the one that is going to be used to calculate the distance. And what do we have? The distance of J is square root of 20, which is about 4.472. Okay, so now let's go back to the business of doing a clustering type algorithm to figure out which of our points are anomalies. And the concept that I want to put across next is the idea of reachability. If you have a point P, the reachability to point Q is defined as the maximum of 2 things: the maximum of the distance from P to Q and the K distance of Q. And so you want a distance, the normal distance, to be small and say that, okay, it is close. And B, you want its K distance to be small, meaning it does have other neighbors around it. Now let's actually put numbers to this. So suppose we take our point P to be A. So we're concentrating on A, and let's suppose the other point Q is G. So what is the reachability of G from A? So 2 concepts are going on here. First, how close is G to A anyway? Okay, that's easy. You can say that G is just distance 2 from A. But then the other thing we want to think about is, are there other points close to G? Remember, we're using 4 for our K distance. So what is the distance of G? Well, when you look at G, the 4 closest points to G are C, B, E, and guess what? A is the 4th one. So it turns out that the distance of G is also 2. So we have a tie. All right, so we shall say that the reachability of point G from point A is going to be 2. Now, that's not always going to be the case. Let's take a look at another example. So this time we're going to say point P is A as before, but let's try to figure out the reachability of L from A. Now, you can see that the distance from A to L is going to be the square root of 2. That's 1.41. Okay, so that's the distance between those 2 points. But then remember, there's the other consideration. Are there other points close to L? So let's figure out the distance of L. Okay, so we've got that the distance of L is square root of 5, which is 2.23. Notice that this time the distance of L is bigger than the ordinary distance of A from L. And so the 2.23 is going to win out, and the reachability of L from A is 2.23. So let's kind of put this together and say, when you're looking at the reachability of a point from another point, you have 2 considerations. A, how far are they from each other? And then secondly, does the other point have companions close to it? Because if it doesn't, that's going to make the reachability get big. So with these 2 ideas, we want to get to a point where we can say, this is a normal point, this is not a normal point. So we want to do a few more calculations. Why don't we start by saying, what's the reachability of every point on our picture from A? So if we do all those calculations, we're going to get something like this. Notice the L has the 2.23 and the G has the 2.0. And then you can see the other points that we have. So let's do it for all the other points. See, this picture shows you that calculation for A. Now do it for B. Now do it for C, and so on. And why don't we take the average reachability around each point? Here's what it looks like. And you can see that points like J, H, F have rather larger figures, and M for that matter, than the points which are kind of clustered together, like the C's and the G's and so on. We actually flip this so that we want the ones that are far away to have the smaller numbers, and the ones that are closer to have the bigger numbers. So why don't we take the reciprocal of all these averages, and we're going to call it the local reachability density. Okay, so we do that, and see, now they've flipped so that the points which are in the far-flung areas like H and J have got the small numbers, and the points which are kind of together have larger numbers. Now that we've got the reciprocal of the average density, we're going to say, take a look at a point like A. It has local reachability density of 0.56. What about its neighbors? Well, B also has 0.56, C has 0.58, which is not much different. L is a little bit lower. Okay, so if I look at the four neighbors of A, they're more or less the same LRD, the same local reachability density as A has. Now think of a point like J. Who are the four neighbors of J? Well, you've got H, okay, about the same. Then you've got M, that's getting to almost twice as much. You've got A, which is actually more than twice as much, and you've got L, which again is much larger. So we're going to say, take the fraction of the average of the LRD of its four neighbors and the point itself. So you're going to take a fraction that will go, take the average LRD of the four neighbors, we're using k equals 4, divide by the LRD of the point itself. Now, from our discussion, if you look at A, for instance, it's got a 1.0. That's because, remember, its neighbors had just about the same LRD. If you look at the point J, it's got 1.85. That is because its four neighbors had LRDs that were significantly larger than that of J. So when you took the division, you got a number that was pretty large. Okay, so now here's the punchline. What we're going to do is to consider the ones that have big numbers to be the outliers, and consider the ones that have smaller numbers to be the inliers, or if you like, the normal versus abnormal points. So we pick a threshold. Let's suppose we pick a threshold like, shall we take 1.5, for example? If we take 1.5, then you've got the 1.85 is high, the 1.81 is high, the 1.99 is high. So those 3 points are the ones we're going to consider outliers. Okay, so in this way, we're able to figure out which of our points are abnormal and which are normal. Okay, so now that you know about unsupervised anomaly detection techniques, please join us for more information on anomaly detection from Learning Tree International.